Welcome to the deep dive. We're here again, taking a close look at your reading list, trying to cut through the noise. Our goal is always to pull out the most useful, the most, impactful bits of knowledge, and often make complex stuff actually click. Today, we're looking at excerpts from visual math. See how math makes sense. The promise is pretty big. Help you stop just memorizing math rules and actually start seeing how it all fits together. So our mission today is to quickly grab those core visualization techniques the text talks about, the keys, supposedly, to understanding equations.
Yeah, and what's really interesting right from the intro is this idea of a whole brain strategies, not just tips. The book basically says you need to use both hemispheres of your brain, like intentionally, to really maximize learning. And it backs this up with a pretty wild statistic. Apparently, sight accounts for something like 75% of how we learn.
75%. Wow. So if math is just symbols on a page, like dense text.
You're missing out massively on 3/4 of your main learning channel.
Yeah.
Exactly. So this visual approach, it's a direct line to tapping into that huge capacity. It makes that old saying, a picture is worth 1,000 words. Well, it makes it the foundation for getting math.
You need the picture to make the logic stick.
Precisely.
Okay, let's dig into that whole brain learning idea then. It seems built around this left brain versus right brain thing. Now, we know everyone uses both, but...
Right. But the text argues one side is often dominant, and that kind of defines how you first approach new info.
Okay, so how does it break them down, the styles?
Well, the left brain is described as, the analyst. It likes things linear, sequential, part to whole.
Step by step.
Exactly. Good with symbols, rules, logic, very reality-based.
And the right brain?
That's more the artist, the visionary. It thinks holistically, maybe a bit randomly, likes to see the whole picture first. It's sensitive to color, feelings, nonverbal stuff. And interestingly, the source calls it intuitive and even fantasy-oriented.
Okay, fantasy-oriented. If math is all logic and reality, isn't there a risk there? Making equations into pictures? Could that mess up the accuracy?
That's a really important question. But the visualization isn't meant to replace reality. It's more like building a strong mental hook, a mnemonic. The logical left brain still provides the rules, how exponents work, the order of operations, all that. The right brain just gives those rules shape, color, context. So you're hitting both sides, the sequence and the overall pattern. That helps lock it into memory.
Ah, okay. That makes sense. It's a framework, not a substitute for the logic.
Speaking of things needing a framework, let's jump into some foundational stuff. Exponents, these can really trip people up, can't they?
Oh, definitely. Often it starts with just identifying the parts. The base is the number we're talking about. The exponent is the power. So like in $45, the 4 is the base. Simple enough.
Right. Where it gets messy is usually with negative numbers. Fine numbers. There are specific rules. If you raise a negative base to an even exponent, the result's positive. Always. Think day D2. That's day type 10 of $8. The negatives cancel. You get 64.
But if the exponent's odd, that last negative sign is left hanging out, right?
Exactly right. Like $13. That's 3 times. D negative $3 and then $3. So it comes out negative. $2.77. You can almost picture it. Pairing up the negative signs. Even number, they all pair up. Odd number, one's left over.
Nice visual. And then there are the operational rules, the shortcuts.
Huge time savers. Multiplying powers. If they have the same base, just add the exponents. So 14 times $43. Easy. It's $42 plus 3 or $45.
And dividing.
Subtract the exponents. Again, same base needed. 528 ties divided by 5 days. So $2 becomes 542, which is $506.
Okay, now for the place where visualization, I think, really pays off. Logarithms. The book calls them exponents in disguise. I like that.
It's the perfect description. And that visual spiral method they show, it's basically a translation tool. You see something like log 2 48 hours. Looks intimidating, maybe.
Yeah, a bit.
But the spiral method tells you, start the little base number, the 2, spiral around past the equal sign to the main number, the 4. It physically traces out the question to what power equals 4.
Ah, and the answer is obviously 2.
Exactly. It turns the log notation directly into an exponent question.
And the source connects this to a real-world thing, right? Chemistry.
Yeah.
pH.
Yes, which is great because it shows it's not just abstract math. Remember the pH formula? It's the negative log base 10 of the hydronium ion concentration. Text log plus
Oh,
T.
whoa, that looks like alphabet soup if you haven't done chemistry in a while.
Totally.
And
But let's use their example. Say the concentration is 10 Li. The formula becomes text pH 10 log 6, 10 6.
Okay, hold on. Use the spiral. What's the log part asking?
The log part 10 6 stays as 10 to what power equals 10 6.
Well, that has to be 6 at all. That's right there in the exponent.
Precisely. So the log part equals 6's calls. But the full pH formula has that negative sign out front. so it's destilar.
which is just 6.
So a measure of acidity, which sounds complicated, just boils down to finding an exponent using that visual trick. That's a powerful connection.
It really bridges the gap between the math function and the actual measurement.
But, and this is a big but, none of this clarity works if you don't follow the rules. Which brings us to PEMDAS, the order of operations.
Please excuse my dear Aunt Sally. Yeah. It seems basic, maybe, but ignoring this structure, this very logical left brain rule,
Yeah.
that's where huge mistakes happen. For math to actually reflect reality consistently, that order parentheses, exponents, multiplication, division, then addition, subtraction, it has to be followed, no exceptions.
And the source gives a killer example to show why it's not just like a suggestion. Take $6 plus 8 times 2, 3 times 5, 5. If you just barrel through left to right, what was the result?
You get 115, which is wildly wrong.
115. That's not a small error. Does that prove math is just arbitrary, or does it prove the order is essential?
It absolutely proves the order is essential. Following PEMDAS, you must do the multiplications first. $8 times 2, 2 is 16. $3 times 5, 5 is 15.
So the problem becomes $6 plus 16, 15, 5.
Right, and that equals 7. The difference between the 115 and 7 isn't just rounding. It's a complete breakdown of meaning because the logical rule was ignored.
Okay, so process matters. Clarity and process. Let's talk clarity and terminology, too. Defining the different types of numbers. We could almost visualize a map here.
Yeah, that's a good way to think about it, like nested circles, maybe
Yeah.
a Venn diagram kind of thing. At the very core, you have the whole numbers. That's 0, 1, 2, 3, the basic counting numbers plus 0.
Okay, simple enough.
Then the next layer out, integers. That's all the whole numbers, plus their negative versions. So negative, -1, 0, 1, 2.
Got it. Positives, negatives, and 0. Then we get into fractions and decimals.
Right, that's the realm of rational numbers. Anything that can be written as a fraction, ratio of 2 integers. Think $12.2, which is 0.5, or $32 thirds, which is 0.333, repeating. If the decimal terminates or repeats, it's rational.
And if it doesn't?
Then it's irrational. These are the numbers that can't be written as a simple fraction. Their decimals go on forever without repeating. Famous examples are T-born or the square root of 2. They just keep going, no pattern.
Seeing them as these distinct groups, yeah, that helps the right brain sort of categorize them instantly. And we should mention that little fun fact. The number 1, neither prime nor composite.
Correct. That trips people up.
Yeah.
A prime number, by definition, has exactly 2 positive factors, 1 and itself. 1 only has 1 factor, itself, so it doesn't fit the definition of prime. And it's not composite either. It's just 1.
Good one to remember for tests, maybe. Okay, let's shift to using these numbers in comparisons.
Yeah.
Ratios and percentages. Ratios, like 3 to 1, are just comparisons. The book suggests visualizing them as groups.
Exactly. If you have, say, a 3.2 ratio of tulips to daisies, don't just picture 3 tulips and 2 daisies in isolation. Think of the total group size. 3 plus 2 is 5. So everything comes in bundles of 5. The total number of flowers will always be a multiple of 5. That group thinking makes proportions easier. If you know your neighbor planted 14 daisies, and daisies are the part of the 3.2 ratio, you can set up an equation. Let the group multiplier be $6, so $2 it goes $14. That means $6 is 7.
So the multiplier is 7. Then you know there are 3 biolubs, which is 21, and the total is $5, or 35 flowers.
Precisely. And this same proportional relationship is why unit conversions work with cross multiplication. You line up the units, make sure the ratios match.
Okay, that makes sense. Now, the big one. The potential disaster zone the book warns about. Successive percent changes.
Yes. This is maybe the most critical warning in the whole text we look at. There are no shortcuts here. None. 0.
Okay, let's walk through the trap. They use an example. An investment drops by 75%, then it increases by 50%. What's the gut reaction the wrong way?
The gut reaction is just to subtract. 75% down, 50% up. Feels like a net 25% decrease.
Yeah, seems logical.
Totally wrong.
Why? Why does simple subtraction fail so badly here?
Because that second percentage, the 50% increase, isn't based on the original amount. It's based on the new, much smaller amount after the 75% drop. If you just assume a 25% net decrease, you're saying 75% of the original value is left. That's not what happens.
Okay, break down the correct way then, step by step.
You start with your original value. Let's just call it V. First, it decreases by 75%. That means you multiply by $1.75 3, which is 0.25. So now you have $4 times 0.255. Then you take that result, the volumes times 0.255, and increase it by 50%. So you multiply by $1 plus 50 cents a mile, which is 1.5.
So the full calculation is original value times 0.25 and then times 1.5.
Exactly. 1 times 0.25 times 1.55. If you calculate 0.25 times 1.55, you get 0.375 for 5.
So after that drop and rise, you only have 0.375 or 37.5% of your original value left.
That's right, which means the actual net decrease wasn't 25%, it was 100%, 37.5%, which is a 62.5% decrease.
Wow. Okay, let's hammer that home. The intuitive guess was a 25% loss. The reality is a 62.5% loss. That's more than double the perceived loss.
Huge difference. It perfectly shows why you must calculate sequentially. The base value changes. Ignoring that takes you completely away from reality.
That is such crucial advice. Fantastic. So we've gone from basic number types through logs using visuals all the way to avoiding that percent change trap, all by focusing on visualization and logical steps.
And it all ties back really to that whole brain idea, using logic and pattern finding together, even in something that feels more advanced, like factoring in algebra.
Factoring, I remember that feeling like pure guesswork. How is that whole brain?
Well, think about reverse FOIL. When you factor something like 6 by dollars plus 6 by 16 equals is doing, you're looking for two numbers that meet two different conditions at the same time.
Okay.
The logical left brain part says, these two numbers have to add up to the middle coefficient, the plus 6. But the pattern-seeking right brain part says, those same two numbers have to multiply to give you the last number, the constant, which is negative 16.
Ah, so I'm scanning factors of negative 16. Like, my next 1 and 16, 1 and next 16, next 2 and 8, 2 and next 8, next 4 and 4. And while I'm scanning those pairs, I'm simultaneously checking, do they add up to plus 6?
Exactly. And you land on plus 8 and actual 2. Because $8 plus natural to 2 equals 66, and 8 times nags to 2, and actual 2 nags to 69. Both conditions met. So the factored form is 6 plus 8 make us $2. That process holding two rules in your head and visually searching for the pair that fits both, that's whole brain learning in action.
That's brilliant. It reframes factoring from guesswork into a structured search using both logic and pattern skills. It makes even complex algebra feel more like discovery, maybe, if you use the right approach.
That's the idea.
Fantastic insights. Thank you for walking us through all this. Hopefully for you listening, applying these visual techniques, minding the order of operations, watching out for those percentage changes, maybe math will start to click a bit more. Until next time.
Happy calculating.